Okay, March 2025, paper 6, variant 2. Question 1. A student investigates the behavior of a spring and then uses a spring to determine the mass of an object. The apparatus is shown. We have a spring, we have a clamp, we have the mass m, and then we have the length L. He suspends mass m from the spring. Describe two techniques for measuring the length of the spring to ensure an accurate reading. You may draw on the diagram. Two of the very important techniques that we can use are to take the reading perpendicularly or to put the ruler close. You can have the ruler, okay, close to the spring, okay, to the spring. Also, it could be parallel to the spring. Okay, parallel to the spring. We can also use a set square. We can use a set square, which is that triangle thingy, which you use to take readings perpendicularly. So basically, it's as if you're saying take the reading perpendicularly to avoid the parallax error. Moving on to question B, we have a table and then we are required to draw or plot a graph of L slash centimeters on the y-axis. Okay, so L slash centimeters and M slash G on the x-axis. The axes, both of them started from the origin from 0 and 0. Okay, so let's start plotting the graph. You have to start from 0. So M, the mass, 100, 200, 300, 400, 500. I guess this is quite easy. You can just plot them. 100, 200, 3, 4, and 500. What about the length? 6, 9, 13, 16.8, 21. So maybe you might think, well, what if I take 5, 10, 20, 5, 10, 15, 20? Would that be a good scale? It wouldn't be the worst, but there's a better scale. So if you use 5, 10, 15, 20, 25, it's okay. But for this scale, we can use a better scale, which would be fours. Okay, we could go up by fours. 4, 8, 12, 16, 20, and 24. Why? Because the largest number would be 21, which is somewhere around here. So yeah, we took up most of the graph on the y-axis and most of the graph on the x-axis. So I guess this would be a very good yeah, plot. Okay, so let's go. First point, 106. 106, it's just, okay, exactly on this point. 106 is here. 209.2. 209.2, this is actually very accurate. Why is it very accurate? Because you'd find 9.2, you'd find 9.2 exactly 3 squares above 8. So 203 squares, if you count 3 squares above 8, this would be exactly 9.2 because every small square is worth 0.4. So 8, 8.4, 8.8, and then 9.2. So this is an exact point, 9.2. 313.6. 313.6. Again, this is an exact point. Why? Because it's 4 squares above 12, or to be more accurate, it's 1 square below 14. So this is 14. Okay, this is 14. It's 1 square beneath it. This is 13.6. Next point is 416.8. Again, this is an exact point, 2 squares above 16, 416.8. Last point is 521. 521, this would be 2.5 squares above 20. 2.5 squares above 20, so at this point. Okay, 2.5 squares. Let's draw a best fit line, and he said that it might not go through the origin, which is quite obvious. Why? Because you have the length against the mass, or the length against the force, which is the weight or the load. We know that the length and the load are not directly proportional. If this was the extension and the load, it would have been directly proportional, but this is the length and the load, which would definitely not go through the origin. It would definitely go somewhere on the y-axis, which would be the initial length of the spring. Let's draw a best fit line. Okay, a straight line. Let's use this. The best fit line would be somewhat like this, maybe extending all the way to, yeah, I guess around this point. So it reached, I guess, around 2.2. Okay, if you say 2.1, 2.2, 2.3, yeah, that would be the y-axis, the y-intercept, around 2.2 or 2.3. Let's go for 2.2. Which is the next question? Which is the next question? Next question, he's asking, use a graph to determine the length and note of the spring with no load on it. So with no load on it, we found that the length is 2.2. So let me remove this line. Definitely you have to keep this line. You have to draw this blue line, which is the best fit line. Okay, you have to draw this best fit line. So the length here would be around 2.2 centimeters. Again, it could differ slightly. You could have a slightly larger or smaller number, which again would be okay. Now we have another spring, probably the same spring. Yes, this is the same spring extended with a different mass. An object X on figure 1.2 measured the stretched length of the spring. If you measure the length of this spring, it would be, I guess, 10 centimeters. It would be 10 centimeters. Again, this would depend on your printer. If your printer prints, if it scales the image up or it could scale it down a bit, again, it would depend on your own printer. So it could differ. It might not be exactly 10 centimeters for you. It could be less, it could be more. Again, we're talking through a small range, but in our actual exams, in our actual final test, we will all have the same exact value. Use your graph to determine the mass mx of object x. How can I use the graph? Okay, so from the graph, I should draw a line from 10 centimeters. So this is 10 centimeters. We need to draw a line. Let's use a different color. If you draw a line, okay, until it hits the graph, I guess it would hit the graph at this point, and then you should draw another vertical line, which is 210 grams, which is 210 grams. So this is the mass of X, 210. Two students measured the mass of another object using the same method of apparatus. One student records the mass of as 132.6. The other student records the mass as 130 grams. State and explain which answer is more suitable. Okay, has the more suitable number of significant figures for this experiment. The more suitable, the more suitable value would be 130. Why? Because all of the values are two significant figures. All of the values are two significant, which is more accurate, which is more suitable for our experiment. So two significant figures is more accurate than two significant figures is more suitable than four significant figures. Okay, good. Now, question 2. A student investigates the effect of insulation on the cooling of water. Okay, he uses the apparatus shown in figure 2.1. Beaker A is covered with a material that is a thermal insulator. Beaker B has no insulation. Record the room temperature theta R. So theta R in this question would be 21 degrees Celsius. 21 degrees Celsius. Describe one technique used to ensure that the room temperature reading is as accurate as possible. We have several techniques. We have several precautions. Okay, one of them is to take the reading perpendicularly. Take the reading perpendicularly. Why? To avoid the parallax error. To avoid the parallax error. Okay, moving on to the next question. Student pours 200 centimeters cubed of hot water into the beaker. Okay, he records the table, repeats the procedure for B. It's important that the temperatures are recorded exactly every 30 seconds. Describe a technique which will make it easier for the student to do that. So how can he exactly record the reading every 30 seconds? Well, by simply leaving the thermometer in the water. Okay, he can leave the thermometer in the beaker. Leave the thermometer, okay, in the beaker. That would ensure that he could take the reading every 30 seconds instead of removing the thermometer and then putting it back in. He could just leave the thermometer for this 3 minutes. It's only 3 minutes, so he'll leave the thermometer for 3 minutes. Write a conclusion stating whether the insulation affects the rate of cooling of the water. Justify your answer by referring to the values from the results. Okay, so beaker A with an insulation, beaker B without an insulation. Beaker A started off with 92.5 and ended at 85.5. What is the difference? Can we find the difference? So A, we'd say 92.5 minus 85.5, which is a difference of 7 degrees Celsius. B started with 93 and ended with 83 and had a difference of 10 degrees Celsius. For this question, you might say yes or no. What do I mean? You can say that the insulation does affect it because it has a difference of 3 degrees Celsius. You might say that that is a huge number. You might say so. And someone else might say, well, no, this is not a huge difference. So it's only 3 degrees Celsius, which is insignificant. So it has no effect. It's insignificant and has no effect. I'd go with that it's insignificant. Again, it's up to you. It is up to you. For this answer, the examiner will probably accept both answers. The examiner would accept both answers because the difference isn't that large and isn't that small. So I'd say that okay, the insulation does not affect the rate of cooling, the rate of cooling, because they're both very close, since the values are very close. Okay, values are close. Question D. Calculate the average rate of cooling during the first half of the experiment. Okay, during the first half of the experiment, theta 0, theta 90 for beaker B. For beaker B, so beaker B started at 93 degrees and at 90 seconds it was 87 degrees. So basically 93 minus 87 divided by the time, which is 90, would give you 0.067. Include the unit. This was the temperature, so it's degrees Celsius, and the time, which was in seconds, degrees Celsius per seconds. Calculate the average cooling at x2 for the second half of the experiment. Theta 90 minus theta 80. Again, theta 90 was 87. Theta 180 was 83. 87 minus 83 minus 83 divided by 90 is 0.044 degrees Celsius per second. Degrees Celsius per second. I soon suggest that for this type of experiment, the temperature of the water in each beaker at time 0 must be the same for the comparison to be fair. Use your answers from DI and II to explain whether this is necessary. Yes, it is necessary. Why? Yes, it is necessary. Why? Let's see. When you had a higher temperature at x1, which was 93, the rate of cooling in 90 seconds was 0.067. When you had a lower temperature at theta 90, after 90 seconds, which was 87, the rate of cooling in the next 90 seconds was 0.044, meaning that the rate of cooling has decreased. So as the temperature of the water decreases, what happens? The rate of cooling also decreases. The rate of cooling decreases as well. Okay. Student wants to eliminate from the comparison any thermal energy lost from the surface of the water. How can he change this? Okay, suggest a change to the equipment which will do that. What should he do? He should use a lid. Use a lid. Oh, quite simple. Suggest what effect this change will have on the cooling rates of the water in beaker A and beaker B. When you use a lid, what will happen to the rate of cooling of the water? Definitely, it will decrease. So the rate of cooling decreases. Rate of cooling decreases. The amount of energy it lost decreases per unit time. Okay, question 3. A student investigates the refraction of light by a transparent block. The student's ray trace sheet is shown full size in figure 3.1. This is a full size diagram. Okay. Student places the transparent block ABCD nearest the center. Okay, draw a normal to point N, extending above AB. Label the upper point of the normal with the letter L. Okay, so let's draw a normal at point N. Okay, above the block. Definitely, you're using your ruler. It has to be 90 degrees, and this point would be L. So again, using a ruler, okay, draw a normal above, okay. He said above, he didn't say extended below, just above the block, L. Okay, and then the student draws line EN as shown on figure 3.1. Measure the acute angle between LN and EN. An acute angle, okay, between LN and EN. He wants to find the measure of this angle. Can I find this angle? Yes, using a ruler. Using a protractor. Definitely not a ruler. Using a protractor, how can I place the protractor? Place the protractor this way. Place the protractor this way. Okay, if we place the protractor this way, it start at 0, and then just find out the angle, which would be around 40 degrees. The angle should be around 40 degrees for this question. Student places pins P1 and P2 on line EN. Measure the distance between P1 and P2. Can I find the distance between P1 and P2? Using the ruler, yes. It would be around 4 centimeters. If you use your ruler, it would be 4 centimeters. State whether the two pins are at a suitable distance or not. 4 centimeters. Is it suitable? No, it's not. Okay? No, not a suitable distance. No, not a suitable distance. Why? Suitable distance. Why? Because we've always said that the distance between two pins on the ray trace sheet should be at least 5 centimeters. Okay? Distance must be, okay? Distance must, okay, must be at least 5 centimeters apart. Or more. Definitely more would be okay. Student views the images of P1 and P2 through the block. Okay, places two pins P3 and P4 so that pins P3 and P4 and the images of P1 all appear exactly one behind the other. Okay, draw a line through P3 and P4, extend this line to meet CD. Extend the line to meet CD. Okay, we'll do that. So using a ruler, P3 and P4, I'm sorry. It's not the best line, but again, you are using a ruler, so it should extend all the way to until it meets CD. Until it meets CD. It shouldn't extend beyond CD. And then label the point to which this line meets CD with the letter F, the lower end of the line G. Okay, so this point is F. This is F, and the lower end would be G. Okay, not bad. And then extend EN approximately 5 centimeters below CD. Label the point at which this line crosses CD. So let's start off by extending line EN to approximately 5 centimeters below CD. We'll just extend this line. Okay, if we extend the line. Again, you're using a ruler, so this must be a very accurate drawing. Okay, 5 centimeters below CD. So you should measure this distance from this point to this point. It should be 5 centimeters. Okay, And then he said, label the point at which this line crosses CD with the letter H. So this is point H. Label the lower end with the letter J. With the letter J. Okay, good, not bad. Measure the angle. Measure the acute angle between CD and GF. Can I find the acute angle between CD and GF? Can I find this angle? Can I find this angle? Alpha, this is alpha. Can I find alpha? Yes, again, using the protractor. Okay, can I find alpha? This would be around, how can I place the protractor for this question? How can I place the protractor for this question? The protractor would be somewhat like this. Okay, okay, centered at this point. We need to measure starting from 0, okay, all the way to this line. So this is the placement of your protractor. Do not draw this blue line. Do not draw this blue line. Okay, so measuring the angle would be around, I guess, 52 or 53 degrees. You should have an angle of around 52 or 53 degrees. Beta, can I measure beta between CD and GH? JH, I'm sorry. Can I find between CD and JH? Yes, I need to find this angle, which is beta. Again, the same for the protractor. This angle would be 50 degrees. It would be 50 degrees. Okay, students suggest that A alpha and beta should be equal. Is alpha equal to beta? Yes, they are. Numerically, they're not equal. But again, are they close? Are they experimentally equal? Yes. How can I calculate it? So 53 over 50 would be equal to 1.06. 1.06 means that there is a 6% difference, which means that they are equal. So the statement, yes, they are equal. Okay, yes, they are equal. Why? Because the values are close. The values are close, and we have to say that they are within the limits, within the limits of experimental accuracy, of experimental of experimental accuracy. Okay. Describe two techniques to use in this type of experiment to ensure that the results are accurate. Two techniques, two precautions. Use thin lines. Use thin lines. And view the bases of the pins. View the bases of the pins. Use thin lines and viewing the bases of the pins. So just one reason why different students all doing this experiment carefully might not obtain identical results. So if you have several students doing the same experiment, they might not find the exact results. So their answers might differ slightly. Why? One very famous difficulty or one very famous problem would be that they are not using thin lines. They are using thick lines, or the lines are too thick. Lines are too thick. That's why we had to use thin lines. This was one of the precautions that we have to say. Moving on to question 4. A student investigates the resistance of a wire, plan an experiment which enables him to investigate how the length of the wire affects the resistance. Okay, this is a very, very easy planning an experiment question. This is a very easy planning. So resistance R equals V over I. Okay, the apparatus available. We have some apparatus, wires, variable power supply, ammeter, voltmeter. I guess we have one very important apparatus which is missing. Yes, he said list any additional apparatuses. We will list the additional apparatus. Okay, complete the figure by drawing a voltmeter connected. How can I draw the voltmeter connected to measure the potential difference across the wire? Okay, so the voltmeter would be in parallel. This is my voltmeter. Explain briefly, okay, state the key variables, okay, the constants, draw a table, and then the conclusion. Okay, let's say it's an easy question. First of all, what is the range of values? what is the independent variable that we are talking about? So basically the range of values, the thing that we will be changing, the thing that you will be changing is what? Is the length of the wire. So we need to we need to state different lengths. Okay, the length of the wire. We can say, for example, 10 centimeters, 10 centimeters, 20 centimeters, 30, 40, and 50 centimeters. You need to state at least five different values. And then after the range of values, you need to say the controlled variables. What are the controlled variables in this question? Can I say the potential difference or the EMF of the power supply? Yes, I can say the voltage of the power supply. Can I say the material of the wire? Definitely. Okay, material of the wire. Can I say the thickness? The thickness of the wire. The diameter of the wire. Yes. The temperature. Okay, we can say the temperature, but for the temperature, we won't be leaving it for that long. But again, you can say the temperature of the wire. Okay, so what are the missing apparatuses? One very, very important apparatus was missing was the meter ruler. We needed a meter ruler to measure the length of the wire, to measure the length of the wire. Okay, let's explain. Okay, let's explain how can we find the resistance for this question. Okay, let's write down the steps. Some very easy steps. For each length of the wire, what should we do? We should measure or take the reading of the current from the ammeter. So take the reading of the current, and we will name it I from the ammeter. Okay, and the reading. Okay, and the reading of the voltage or potential difference V from the voltmeter. From the voltmeter. Okay, so you have the voltage and the current. Calculate the current, calculate the resistance. Calculate the resistance. R equals V over I. R equals V over I. That's it. That is it. And then we will say repeat and take average. Repeat and take average. Okay, that's it for the steps. Okay. These are the steps. Okay, can I draw a table? Yes, I can draw the table. Okay, I don't need a very long or a very huge table. A very small table would be sufficient. What are the readings that we're taking? We have several readings in this experiment. We have, first of all, the independent variable. What was the independent variable? So it's the length. It is the length in centimeters. And then the voltage in volts, and the current in amperes. And last but not least, the resistance in ohms. The resistance in ohms. Okay, so now we have written down the steps, we have the table. What is the conclusion, or what is one conclusion that I can write down? It's a very systematic conclusion. Okay, conclusion. For each value of length, okay, or for each length, for each length of the wire, repeat the experiment and take average, and then record the readings, in the table. In the table, and then all you need to say is to compare the results. Okay, compare the results by drawing a graph. By drawing a graph. And that's it. That is it. Okay.